The next application of the derivative we're going to cover is curve sketching. We're going to see how we can use the first and second derivatives to sketch a graph of any curve. We're going to focus on polynomials, but these rules apply to any curve. And all of these results, in order to get there, we're going to need to cover a few large results in calculus, and they'll all be called theorems. But all of these theorems are actually consequences of the mean value theorem. The mean value theorem, remember, tells you, the statement of the mean value theorem tells you about the derivative at a point. But the choice of A and B in the statement of the mean value theorem, the endpoints of the interval, can be moved all over as long as the function remains continuous and differentiable, meaning, it looks like a curve with no corners and it's all in one piece. And because we can move that A and B, we can use the mean value theorem to reach conclusions about the derivative on entire intervals, not just points. And this first theorem covers a consequence of the derivative on an entire interval. So first, let f of x, let f, and we don't need the of x here, so I didn't write it. Let f be continuous on a to b, closed, differentiable on a to b, open. Then, two parts. One, if the first derivative, if f prime is greater than 0 on a to b. If the first derivative is positive on a to b, then f is increasing. Now, we haven't really discussed increasing, or in part 2, decreasing. Increasing just means going up as x gets larger. Decreasing means going down as x gets larger. I'm not going to formally define those. But part 1, if the first derivative is positive, then f is increasing. Part 2, if the first derivative is negative, then f is decreasing. I like this result because it relates positive and increasing. Both of those are, in my mind, positive sounding words. Well, positive sounds awfully positive, but increasing is also a positive sounding word. If f prime is negative, then f is decreasing. So we have positive derivative tells you the original function is increasing. Negative derivative tells you the original function is decreasing. And notice the form that, oh, that's not a sentence. This then shouldn't be there. Notice the form of these two sentences, 1 and 2, are if-then statements. Our assumption in both is an assumption on the derivative. We're making an assumption on the derivative, and the conclusion in both is on the original function. So a property of the first derivative allows you to conclude useful information. Well, we'll see it's useful to this point. Why is this useful? Well, we'll see. But it allows you to conclude useful information on the original function. Our goal here is going to be to use the first and later the second derivatives to sketch a graph of an original function. So here, a property of the derivative lets you reach a conclusion about the original function. Let's just look at this example illustrating that directly. Example, given the graph of f prime. Right here is a graph of f prime. Not just f, it's f prime. Given this graph, identify intervals on which f of x is increasing, identify intervals on which f of x is decreasing. Inc, dec, increasing and decreasing are long words. Plus I didn't want to take up too much more space with the statement of the example. But here's a graph of f prime, and it goes through the x-axis at 1, or at -1 and 3. And the theorem over there says if the first derivative is positive. Notice we're not including the endpoint. Well, I'll mention that after I write the answer. If the first derivative is positive, then the original function is increasing. So where is the first derivative positive? Well, it's positive where it's above the x-axis. Here, this is above the axis between -1 and 3. So f is increasing on -1 to 3. It's decreasing wherever the first derivative is negative, according to part 2 over there, where the first derivative is negative. The original is decreasing. It's negative over here and over here. So it's decreasing on negative infinity up until negative 1, together with 3 up to infinity. Well, maybe I should say on to infinity. Up to infinity would imply it stops, I think. So notice in this example, we don't include the endpoints. At the endpoints negative 1 and 3, notice the first derivative is 0. This theorem doesn't tell you anything about what happens when the first derivative is 0. It just tells you about what happens where the first derivative is positive. Now, why doesn't it tell us about what happens at 0? Well, we'll examine that a little more closely. But notice, up until this point, we can't use calculus to differentiate between a local maximum and a local minimum. Why is that? Well, look at these two curves. Move the eraser because I didn't think I needed it. Then I need it a minute later. Here we have a local maximum. Here we have a local minimum. Where is the local maximum? Well, remember, a local maximum is up there at the top of a mound. A local minimum is at the bottom of the mound. Now, why can't we use calculus to differentiate between these? Well, notice in both cases, well, recall, I guess, in both cases, the derivative is 0 there, or undefined if these, meet at a point rather than, smooth mounded curve. So in both cases, maybe I'll write it between them. In both cases, let's call this f, f prime equals 0. Let's say this is local minimum. Technically an absolute as well, but we're just looking at the local property. And this one's the local maximum. So from the graph, we can just look at that and say, well, that's a local maximum. From this graph, well, that's a local minimum. But we would like to differentiate between these two using calculus. And notice until now, we can't, because in both cases, the derivative is 0, or undefined if they happen to meet at a point where it's non-differentiable. But we would like to differentiate between these. Learning how or seeing how we can differentiate between them might be useful if we want to sketch a graph. And fortunately, the following theorem will differentiate between these two cases. Theorem. We'll call this the first derivative test, because we're going to use information on the first derivative to reach the conclusions that we want. Before I state the theorem, I'd like to describe these two graphs again that were, from a few seconds ago in the video. But they were drawn differently on these two boards. I just moved them to that. Why can we use the first derivative to differentiate between these? Well, the first theorem we covered here told us what derivative properties would lead us to conclude a function is increasing or decreasing on an interval. And we can differentiate between the local maximum and the local minimum by observing where the function is increasing, where it's decreasing. Here, for a local maximum, the function, if it has a local maximum at a point, and again, this could be, a corner up there, but if a function is increasing on this side, and then after, so in both of these cases, the first derivative was 0, but, or undefined. But if it's increasing on the left and decreasing on the right, then between them you will have a local maximum. And similarly over here, the function is decreasing as it gets to the local minimum, where the derivative is 0 or undefined, and it's increasing afterwards. And we, with that previous theorem, can describe those situations using calculus. And we call this the first derivative test. So let's state the first derivative test, 3 parts. Let x be a critical point of f. So we have a function f and we have a critical point. A critical point we didn't define yet, but notice from here, a local maximum could look like that, could look like that. And a critical point is one of those points, or the same thing upside down. But it's a point where the derivative is 0 or the derivative is undefined. If last week I got through 5 more minutes of extreme value theorem discussion, I would have defined that, but well, I'm defining it here. Let x be a critical point of f, and then here's the definition. A critical point is an x value at which the derivative is 0 or undefined. Most conveniently described by these 4 graphs that I erased, just erased. 1. If f prime is positive to the left of x, and f prime is negative to the right of x, then f has a local maximum at x. And we can see that with this first graph up here. If f prime is positive, then f is increasing. So over here, f prime is going to be positive. And similarly on the right of x. If the derivative is negative, we will have that the function is decreasing, and then we will have this situation where that critical point will be at the top of a mound, because a function is increasing and then it switches to decreasing. In the middle of those will be a top point. So if f prime is positive to the left, negative to the right, then we have a local maximum at x. Part 2 is the same thing, except describes this situation. If f prime is negative to the left, positive to the right, then f has a local maximum. Those 2 statements, a lot of left, right, positive, negative. I think they're easiest to describe with this picture. With this picture and that first theorem we covered in this video, we have a nice relation between the signs of the derivative and increasing and decreasing. So I'm never going to ask you to state a result like this, but having the calculus interpretation of that result is very important. Now part 3, these first 2 graphs here illustrate parts 1 and 2. Whoa. Good thing I read that. Local minimum. Sorry about that. I don't know how that happened. Hopefully you caught that when you were writing. I noticed this says maximum twice, and I said that second graph describes the minimum situation. If decreasing to the left, increasing to the right, we have this situation where we get a local minimum. Now part 3, right here, these first 2 parts describe what happens when the first derivative changes sign. But what happens if the first derivative doesn't change sign? That can happen. What kind of interpretation can we make? If f prime has the same sign on both sides of x, then f does not have a local maximum, and f does not have a local minimum at x. F does not have a local maximum or a local minimum at x. What does that look like? So I'll just say illustrating 3. So those first 2 graphs there illustrate, let's walk into a table, good job, illustrate 1 and 2. What would 3 look like? Well, I'll same sign, you could have positive, positive, or negative, negative. I'll draw positive, positive, negative, negative, just, flip it around. Something like this. Case 3 applies. Right in here, we do have a horizontal tangent line. If you want an actual function, you can make this, I guess we're using functions, maybe I should call it a function. F of x equals the x cubed function moved around a little, so x minus 2 cubed plus 5, I guess. And right here, at 2, the function does not have a local maximum and it does not have a local minimum, but also notice that the first derivative over here is going to be positive. And the first derivative over here is also going to be positive. The function is increasing on both sides. And if it were negative, we could just flip it around over a horizontal axis. Another example you could look at, just instead of throwing all these numbers around, take f of x equals x cubed at x equals 0. X equals 0 would be a critical point for that, and, well, we could even show this. F prime of x is what? 3x squared equals 0 when x equals 0. There's its critical point. And why does case 3 apply? F prime is positive on the left and right of 0. So directly applying case 3 instead of just throwing a graph down. F prime is positive on both sides. Why? Well, it's 3x squared. It's positive everywhere except 0. But when the sign of the derivative changes, we can see that using calculus. We can see what it means using calculus. So we've described the first derivative. We've gotten some nice information using the first derivative. Let's next analyze the second derivative. What does the second derivative measure? Well, to figure that out, let's remember what the first derivative actually is measuring. Recall, the derivative measures a rate of change. And we have this fractional notation dy dx. One of its conveniences is that it makes the chain rule feel more algebraic. Another convenience is that we can interpret the derivative as telling us how y is changing as x is changing at a given instant. But, we can move that instant all over the place. So in general, dy dx, the derivative, tells us how y is changing as x is changing. And we can see that nicely as the slope of the tangent line. Well, the slope in a derivative context means the slope of the tangent line on the second board. That's how I use it. But we can understand that instantaneous change as the slope of a tangent line. Well, the second derivative is just the derivative of the derivative. So we're taking the derivative of a derivative. Well, a derivative measures a rate of change. But here, we're measuring the rate of change of the first derivative. We're measuring the rate of change of these slopes of tangent lines. So the second derivative is going to tell us how the slopes of the tangent lines are changing. And let's observe these four graphs. So these two are going to go together. These two are going to go together. So I wrote observe twice, so you didn't do 1, 2, 3, 4. It's actually 1, 2, 3, 4. But what are we going to observe? Well, we're going to look at how the slopes of tangent lines are changing. Oh, that marker works wonderfully. Wow, that works only okay, but I guess it works better. Let's look at the derivative at that point. I guess I'm going to call all of these f. We're going to have four functions. Let's just call them all f. Where is f not going to be in the way? I guess there it won't be in the way. This one I'm going to move up here. This one I'll move up here. This one, well, I'll put it up there. This one I'll put up here. These are all going to be f. There's no reason to call them f1, f2, f3, f4. That's way too many extra numbers. But what is the slope of the tangent line here? Well, the slope of the tangent line there is the slope of that line, and I'm going to draw that smaller. The slope, the derivative, f prime, is the at that point is the slope of that tangent line. Well, how does that relate to another derivative. The second derivative we're going to use to figure out how the slope is changing. So let's look at how these slopes are changing. So over here we have a positive slope. Over here we have a more positive slope. So here we have slant. Let me get my flag so I can use that for my tangent lines. The blue part is always supposed to be on the upper left, so okay, yeah, that's right, as far as the camera is concerned. So here, at this point, right here, we have a positive slope. Over here, we have a more positive slope. So right here, the slope is changing in a positive way. It's going from positive to more positive. Keep that in mind. It's changing from positive to more positive. Maybe I'll write something like that. Slope is positive. Slope is more positive. And you can see that if you let your tangent line travel through, we're starting with a lowish positive number, and it becomes more slanted upward. The slope is getting more positive. Well, let's look at this and then I'll say what I was going to say. Let's look at the same thing here. That's a terrible tangent line. Let's look at this tangent line. We have here a negative slope. A negative slope. It's going downward. How about over here? Well, we also have a negative slope. But notice it's less slanted downward than this one. And you can let these tangent lines travel along this curve, and you notice they start as a negative slope, a very negative slope, and they keep gradually getting less negative. So in that first case, slope started positive and got more positive. Here, the slope started as a negative and became less negative. So both of those are actually describing the same difference in slope. Because we're starting as a positive and getting more positive. We're starting as a negative, we're getting less negative. Both of these changes are in the positive direction. So if you have, a number line with negative infinity off that way, positive infinity off that way, these slopes are traveling in this direction in both of these cases. And because of that, the second derivative is going to, because the second derivative tells us how the slope is changing, the second derivative is going to see these two as the same. And we're going to formally define that in a moment, but let's look at the opposite case. So here we have positive getting more positive, negative getting less negative. Well, these other two are going to describe the other two choices, but why? Well, let's look at it in a little detail. Here, we have that slope, and let's compare it to that slope. What do we have here? A very positive slope getting less positive. A very positive slope getting less positive. So we have a very positive getting less positive, so slope is positive, slope is less positive. So I'll just say, so I have two sentences, well, two remarks there, two phrases or something. Oh no, those are sentences, I guess, sort of. I'll just combine them as one here. Slope gets, what did I say? Starts as a positive, gets less positive. And what happens here? Maybe I didn't need F for these. Well, for the next theorem I write, I will refer to an F. What happens here? Well, flag unravels. What happens here? Slope is a negative. It's only moderately downward slanting, so it's a smallish negative, so it's a negative number kind of close to 0. But over here, the slope is very negative. So here, we start as a negative, and it gets more negative. So you know, I probably should have mentioned this at the beginning, I am writing these words on this side of the curves in each case on purpose. So here, slope gets more negative. So slope gets less positive, slope gets more negative here. Both of those describe the same action. If we have our real number line, negative infinity off to there, positive infinity, I guess I had it like this before. Negative infinity off to there, positive infinity off to there. Getting less positive and getting more negative describe actions in the negative direction. And because of that, the second derivative is going to see these as the same. This first situation, we're going to define as concave up. When one of these two happens, it will be a concave up. The function will be concave up. And in this other case where the slope is changing in a negative way, we're going to call it concave down. And why do we call it these words? Well, because we can see without going through a slope analysis, we can see how the function is kind of caving. Well, here, what do I mean by that? We'll take the bowed in part of the function and point away from the bowed in part of the function in all cases. Bowed in meaning, you know, like that's exaggerated, but like that. Point away from that piece in all cases. You know, I just drew this, and from this angle that looks like a face with eyebrows and a long arrow for a nose. They should all look the same, but just from that perspective it looked like that. Now this one looks like that. But we're going to call them concave up, concave down. Why is that? Well, when we point away from the bowed piece, bowed in piece maybe I should say, bowed, B-O-W-E-D is the word I'm saying. But we point away from that. In both of these cases, those arrows are trending upward. And if you look at these two cases, both of those are trending downward. So we call this one concave down, and concave up is the first one. Now, this is kind of a tedious argument to conclude a function is concave up, concave down, looking at the slope being positive, the slope getting more positive. Now, in both of those cases, we could use the first derivative to reach these conclusions. Because the first derivative, the slopes of the tangent lines, are changing in a positive way. The first derivative in this case over here is positive. Scratch that. The first derivative in both of these cases over here is increasing, because the slope is positive and it's getting more positive. So the first derivative is getting larger. In this case, it's negative, getting less negative. The first derivative is still trending upwards, still increasing. And similarly over here, we could describe this by saying the first derivative is decreasing, because the slope starts out very positive and gets less positive. So the first derivative is decreasing, and down here similarly, it's negative getting more negative. The first derivative is getting smaller. It's decreasing. So we would have a result if the first derivative is increasing, function's concave up. If the first derivative is decreasing, the function is concave down. But how can we figure out if the first derivative is increasing or decreasing? Have we seen any theorems which allow us to figure out when a function is increasing versus when it is decreasing? If it's increasing, we're here. If it's decreasing, well, maybe I'll point to, if it's increasing the first derivative, we're here. If it's decreasing the first derivative, we're here. Can we figure out when the first derivative is increasing or decreasing? Well, we can. The first theorem we covered here allows us to conclude when the first derivative is decreasing. So what we can do is take that first theorem, put extra primes on everything. Then it would be if f prime prime is positive, then f prime is increasing. If f prime prime is negative, then f prime, the first derivative, is decreasing. And we're going to call that the second derivative test. I'm going to write that down, because it'll be more clear to see it than to hear it, I think. The second derivative test. Let f be differentiable, diff period, differentiable, on a to b. Two parts. First part, if the second derivative, f prime prime, is positive on a to b, then f is concave up on a to b. And that follows from the previous discussion, where we applied the first theorem of this lecture to the second derivative. The first theorem said, in general, if a derivative is positive, then the function itself is increasing. So technically we're applying the first theorem to the first derivative rather than just a function. But applying the first theorem to reach conclusions about the first derivative, we were able to see that when the second derivative was positive, the first derivative was increasing. And when the first derivative was increasing, we were in one of those two situations on that graph where we had concave up. So bypassing that first derivative observation, we can conclude, and that's why we call this the second derivative test, we can conclude if the second derivative is positive, then the original function is concave up. And again, we are bypassing all first derivative observations in this statement and part 2. Part 2 just flips that around, because all these results have a positive sign, or all these results have two parts, a positive part and a negative part. So here, if the second derivative is negative on a to b, then the function is concave down on a to b. And, well, I'll mention that in a moment. But notice here, we do have second derivative positive, concave up. Second derivative negative, concave down. Positive up, negative down. Now, what happens when concavity changes? What does it look like when concavity changes? Because with the first derivative, we were able to visually see, that's redundant, what happened when the signs of the first derivative changed. When it went increasing to decreasing, we had this local maximum. When it went decreasing to increasing, I guess it goes this way, decreasing to increasing, we have this local minimum. What happens with concavity? Well, we'll see in a moment that we need the function to be continuous to see what we want to see. And we'll define that here. If f is continuous at x and changes concavity through x, meaning it's concave up on one side, concave down on the other, then we say f has an inflection point at x. And we'll see why we need this continuous assumption in a moment. But let's look at what an inflection point looks like. So here we have this function. Where is it concave up? Where is it concave down? Well, where are the caved-in portions pointing upward? Where are they downward? Well, here we have some caved-in portions like that. And where do these change? Well, they change right in the middle where it's no longer pointing downward, the caved-in portion, and it switches to pointing upward. They change at a value like this. We'll call it x. So here, x, well, maybe I'll say here, F is concave up on where? Concave up, that's a pretty long word, so CC arrow pointing up, that's 4 arm strokes, well, maybe 5 depending on your arrows. Concave up itself is a lot more than 4 arm strokes. And down, that's an even longer word. So CC arrow. Here F is concave up where? Where it's pointing up. So on x to infinity, not including x, because it's neither concave up nor concave down there. And here it's concave down on where the caved-in portion is pointing downward, negative infinity up to x. But also, the concavity, notice, is changing at x. So F here has an inflection point at x. So I'll just say and F has an inflection point at x, because that concavity changes. Now, why do we need this continuous assumption in order for there to be an inflection point? Well, so y is continuous necessary for an inflection point. Well, let's just look at this curve. We've seen this one before. F of x equals 1 over x. I should have written that in the second quadrant. So if you didn't write it yet, hopefully you can move that over to the second quadrant. F of x equals 1 over x. Notice it's concave down. So CC, let's do up first, on where? 0 to infinity. Concave down on negative infinity to 0. But there's no inflection point at 0. So the concavity is changing through 0, but it wouldn't make sense to say there's an inflection point because, here's a point. It makes sense to describe that. Here, there's no point occurring where the concavity changes. So I'll just say but. I'll just say no inflection point. I'm not really writing a sentence for this example. So no inflection point. And inflection point, just like concave up, concave down. Those are long words. You may have noticed in this lecture, we do have a lot of words that we've covered. So who needs to write an extra, 10 letters or something? 11 letters. No, it is 10. I forgot about the T. But we've covered many results using the first and second derivatives. And our goal here, remember, is to sketch graphs using calculus. We want to sketch graphs. And we've covered several results on graphs. But let's consolidate all of those results we've covered into 4 graphs that we will see next. Remark. This will be a long remark. It spans all 4 boards. It's not the end of the sentence yet. The sketch of a graph can be found by identifying intervals over which f, the function you want to sketch, looks like one of these 4 curves. And on the second board, there is this glare here, but there's nothing written underneath it except maybe part of the y-axis. But the function is, the curve we're looking at is over here. Now, we're using 5 different f's here. I'm calling each of these f, I'm calling each of these f, and I'm calling the curve we want to sketch an f. I don't think that will lead to confusion. But the sketch of a graph can be found by identifying intervals over which f looks like one of these 4 and piecing together the result, which I'm going to write in a moment after I write some other thing. So we have these four curves. We saw these four curves before when we were getting to concave up, concave down. But we can do more with those curves. We can fully describe these curves using the first and second derivatives. Why? Well, let's do it in words first, and then let's turn that into derivative results. Here, f is, and I don't need is's, I'll write 8 is's if I have to do that. So let's not use is's. Here, the function is increasing, it's going up. But it's also, well, let's do increasing, decreasing for these other. Here, the second one, f is increasing as well, it's going up. What about here, in the third one? Here, it's going down. F is decreasing. What about here? Well, f is also going down. So f is decreasing. What about concavity? Here, that's going up. F is concave up. What about here? That's going down. F is concave down. What about here? That's going up. So that's concave up. And here, that's going down. So we've described these functions, we've differentiated between these four functions by describing whether they're increasing, decreasing, whether they're concave up, concave down. But with the previous results, we can do more. We can describe both of these using the first derivative. So here, the first derivative is positive. The function's increasing, and, well, where the function is increasing, first derivative is going to be positive, and where it's decreasing, the first derivative will be negative. What about concavity? Well, actually, for those first derivatives, I should have been saying where the first derivative is positive, the function is increasing. Where the first derivative is negative, the function is decreasing. What about concavity? Where the second derivative is positive, the function is concave up. Where the second derivative is negative, the function is concave down. So we could also differentiate between these curves by looking at the signs of the first and second derivative and figuring out which one of these four curves exists on each interval, and then we piece together the result. So to finish the sentence, the remark, and piecing together, good job spelling piecing. That was directed at me, I'm not looking at how you're writing the word piecing. P-I-E-C-I-N-G. Together, the result. So, total remark. The sketch of a graph can be found by identifying intervals on which f looks like one of these four, which we can do using the first and second derivatives, find where they're 0, find where they're positive, find where they're negative, and piecing together the results. Piecing, identifying, okay, tenses work. So, to do this, we need where the first and second derivatives are positive, where they're negative, and then we need to go back to these graphs and piece together the result. One other thing we need, which I didn't write, but we will do in the examples, we're also going to need a starting point. More on that when we do examples, which will be next. Examples. Sketch a graph of each of these functions. Directions could say, use calculus to sketch a graph. I'll probably phrase it something like that on the test. We're going to use calculus to sketch these graphs. Well, how do we do that? Well, let's start with A. Remember, we're going to figure out where the function is, where the first derivative is positive, where it's negative, and the same for the second derivative. So to do that, we need the first derivative. We'll start with part A. 3x squared, negative 12x, positive 9. Where is that positive? Well, it's positive not where it's 0, but where it's 0 breaks it up into where it's positive and where it's negative. So we need to find where it's 0. Well, factor out of 3. Those all have 3's on them. Does this factor further? Well, yeah, 3 and 1 make 4, 3 and 1 make 3. I should probably write 1 and 3. So x minus 1, x minus 3. Want to set that equal to 0. When is this 0? When x equals 1 or when x equals 3. We found where it's 0. We can use that to find where the first derivative is positive and where it's negative. And how can we do that? Well, I'm going to draw it like this. I'm going to draw a number line. I'm going to break it at 1 and 3. So at 1 and 3, I'm going to move 1 and 3. So at 1 and 3, the first derivative is 0. So that means over here, it's on one side of 0. In here, it's on another side of 0 potentially. On here, it's on another side of 0. Positive or negative side of 0. We just need to figure out in each of these intervals whether the first derivative is positive or negative. And how can we do that? Well, we can evaluate the first derivative at a point in each of these intervals. Let's do it like this. Let's do it like this. F prime. Let's start over here. Here we're on the interval negative infinity up to 1. Pick a value there. Let's say 0. 0's in there. Evaluate this at 0, or evaluate the derivative at 0. Well, you could substitute x equals 0 here and count signs. With 0, it's generally easier to just jump here. F prime at 0 is 9. 9 is a positive number. Remember, the fact that it's 9 isn't completely relevant. The fact that it's positive is completely relevant. So we picked a point over here. We picked the point x equals 0. Evaluated the derivative. We got a positive number. And let's do that for the others as well. F prime here. Pick a number between 1 and 3. How about 2? 2 works. And instead of substituting here, I'm going to substitute down here and count signs. Because remember, the sign is all that matters. Substitute x equals 2, positive times negative. Substitute x equals 2, positive times 1 times negative 1. So we got a negative. And similarly, we're going to go on in this interval. Pick a number like 4. Substitute x equals 4. You get positive times positive times positive, which is positive. So we have where the first derivative is positive and where it's negative. So our original function is increasing where the first derivative is positive and decreasing where the first derivative is negative. There are a few different ways you can notate this, if notate is a word. I like to do it like this because this number line now tells us where the function is increasing or decreasing. We used information we got from the first derivative to reach conclusions about the original function. The original function is increasing on this interval and that interval and decreasing on that interval. So let's do the same thing with the second derivative. We're going to do the same thing and we're going to, it's going to look almost identical what we're doing. We're going to get another number line. For board organizational purposes, I'm going to draw the number line down here, and I'm going to do the algebra over here. It may look a little different in your notes. F, second derivative, is what? 6x minus 12 plus 0. So 6x minus 12, when is this 0? Well, that's 0 when x equals 2, because 12 minus 12 is 0. And that's the only place where it's 0. So mark it off at 2. And now we need the sign of the second derivative. The second derivative at a point over here, say 0. The second derivative at 0 is negative. 0 minus 12, which is negative. The second derivative over here, on that side of 2, pick a number like 3. Let x equal 3. You get positive 6, which is positive. So the function is concave up where where the second derivative is positive, and concave down where the second derivative is negative. And now we're almost ready to sketch a graph. Why almost? Well, why almost indeed? Why almost? Remember, we're piecing together curves like this, like this, like this, and like that. Great summary of an hour of calculus. That curve right there, that's astoundingly similar to what this is going to look like. This isn't this. I was just drawing a swiggle. This curve right here has those 4 pieces. It has this piece, it has that piece, it has, it has that piece, it has that piece, it has that piece. And it's on certain intervals. You know, certain x values break it apart. This one is supposed to be drawn wavy parallel. This one has the same intervals on which the function looks like those 4 pieces. It has this piece up to that x value, this piece up to that x value, this piece up to that x value, and this piece for the rest. Now, what does this mean? Well, it means the calculus we've done can't distinguish between those 2 curves. But what we can do is find a point on those curves which will allow us to differentiate between them. And a very convenient point, especially with polynomials, to find is the y-intercept. 1, 2, and 3. So we will find the y-intercept to give us, in a sense, a starting point. But even before that, I like to just mark off these numbers, 1, 2, and 3. Because that's going to tell us where our function breaks apart. Meaning where it switches from one piece to another. Y-intercept is 30. Let's say that's 30. I'm going to label it 0, 30 in a moment once I draw a curve. Now, how do we piece together the results? Well, we've broken our x-axis into 4 intervals. Negative infinity to 1, 1 to 2, 2 to 3, 3 to infinity. First interval, negative infinity to 1. What happens there? Well, we go back to our number lines. This is another reason I like these number lines. On negative infinity to 1, increasing. Concave down. What does increasing concave down look like? No. No. You'd think I'd be able to do that immediately. Increasing concave down. Yes. Increasing concave down. So we put one of those pieces on negative infinity to 1, going through that point. And we'll make it go to negative infinity. So we take one of those pieces. Well, so we noticed we're on negative infinity to 1, increasing concave down. We took one of those pieces, increasing concave down, and we put it there. And we're going to do that for the rest of the interval. So 1 to 2, decreasing concave down. No. Yes. decreasing and concave down. And we put that from 1 to 2. Like that. Next interval, 2 to 3, decreasing, concave up. Let's see if I can get it right the first. Decreasing, concave up is one of those. Decreasing, concave up. Put one of those from 2, that's terrible. Put one of those from 2 to 3. Like that. That doesn't look enough like it. Zero, 30, one of those, one of those, put one of those from 2 to 3. Oh, I can't draw that here. Maybe I didn't give myself enough space. Let's move 2 over a little. There. Maybe if I did it like this. That's slightly better. But there is one of those pieces there, from 2 to 3. And now, from 3 to infinity, our last piece, we're increasing, we're concave up. Increasing, concave up, looks like that. So we'll put one of those here. Increasing and concave up. And here we have a sketch. Now with these sketches, you don't have to worry about exactly where it intersects the x-axis. Just worry about the calculus. But do worry about the y-intercept, because it is important to observe that the calculus does not differentiate between this and something like this shifted up 10 units. Because the derivative of a constant is 0. So at that point is 0, 30. And this is f of x. Now there are some other things we could do with this graph. These directions don't say any of it, but you could. I could ask you something like label the local maximum, label the local minimum. Well, there's a local maximum. There's a local minimum. Label the inflection point, or label inflection points if they exist. All of these are if they exist. Inflection point where concavity changes and it's continuous. Here concavity changes and it's continuous. We're going to be sketching only polynomials, so it'll always be continuous. Why is this a local maximum? Well, look at the graph, or use the first derivative test. Increasing to decreasing. The first derivative goes from positive to negative. So there are a few different things you could be asked about these beyond just sketching them. Let's do the second one. Part B. F of x equals 2 plus 3x squared minus x cubed. Well, what's f prime of x? I'm going to write it over here. I like putting the number lines down here. I'm going to continue with that in case the graph takes 2 pages. F prime of x, 0 plus 6x minus 3x squared. So 6x minus 3x squared. We want to set this equal to 0. We can first factor it a little. We can pull a 3 off of everything. We can pull an x off of everything. We're left with a 2. We're left with a negative x. And when is this 0? Well, it's 0 when 3x equals 0. It's also 0 when x equals 2. So now we have points 0 and 2 for our first derivative. What is f prime over here? Well, on this interval, let's pick a number. -1 set. Evaluate at -1, and you could jump here, find a number again. I would generally steer toward the factored form. X equals -1. We have a positive, or sorry, we have a negative times a positive. Negative times a positive is a negative. F prime at 1. Positive times a positive, which is positive. F prime over here at, say, 3. At 3, you have a positive times a negative, which is a negative. So the function is decreasing over here, it's increasing in here, and it's decreasing over there. Let's do the same with the second derivative. What's the second derivative? Let's put an of x, because that's what I've been doing for these computations. Second derivative, we have 6 minus 6x. When is that 0? When x equals 1. Because 6 minus 6 is 0. So break the interval at 1. F second prime on the left of 1, let x equal 0. F second prime is positive. On the other side of 1, pick a number like 2. 6 minus 12 is negative. So let's write a less than instead of a greater than. Where the second derivative is positive, the original is concave up. Where the second derivative is negative, the original is concave down. So let's piece this graph together. First, we notice which x values are going to matter. 0, 1, and 2 in this case. Here's 0, here's 1, here's 2. What's our y-intercept? Our y-intercept is at height 2. So right there, let's call it 0, 2, and let's not put it there, and I don't need that long of an x-axis, or y-axis. Let's put the ordered pair later. So our first interval, negative infinity to 0, decreasing, concave up. One of those. Decreasing, concave up. That's going right through the middle of that point. Next interval, 0 to 1. Increasing, still concave up. Increasing, concave up. Looks like one of those. Put one of those from 0 to 1. 1 to 2, increasing, concave down. You know, you may notice if you go frame by frame, which on YouTube is what, the period and the comma, you might notice, I believe I started shaking my head even before I started drawing that, because I knew I was drawing the wrong one before I drew it, but I still drew it. What did I say? 1 to 2. Yeah, there are many YouTube shortcuts that are useful. K pauses, L goes forward 10 seconds, 20 seconds if you double up the time, and J goes back 10 seconds. Those are the only ones I know, I think. 1 to 2. Increasing, concave down. What's increasing? Going up, concave down. So it's one of these. Increasing and concave down from 1 to 2. So it looks like that. And then from 2 to infinity, it changes to decreasing and remains concave down. Looks like one of those. And if you draw a point like that, you might want to just round it out. There, that looks better. So there's a sketch of f of x, and this y-intercept was what? 0, 2. And again, you could be asked to label local minimum here. Local minimum occurs at 0. Here, a local maximum occurs at 2. And here, an inflection point occurs at 1. That says an x. Local maximum. Here, I don't believe I'm going to ask you to find the ordered pairs unless it's a y-intercept. You know, finding an ordered pair is, it's really just a pain. So I usually don't ask things that are just a pain unless they're calculus. Not to say calculus is a pain, calculus is interesting. C, f prime. Or we need f prime of x. First and second derivative, where it's 0, where it's undefined. F prime here, negative 4x. plus 5. We want to set that equal to 0. It equals 0 when x equals, what, 5 quarters? Yes, when x equals 5 quarters, put 5 quarters there, 4's go away, negative 5 plus 5 is 0. So we'll break our interval. Here we have only one point that we're breaking our interval on, 5 quarters. F prime on this side, so let x equal 0, f prime is positive. F prime on this side, let x equal, say, 10,000, negative. You know, if you don't want to think, well, if you have a fraction, you don't want to think of where the fraction actually is, you know, just pick a number way away from it that's still in the interval. 10,000, you get negative 39,995. 39,999, yeah, okay, that's the right number of nines. Yeah. 39,995. Yes, okay. I wasn't sure if I said too many nines. So the function is increasing over here, and it's decreasing over there. Let's do the same thing with the second derivative. But here, notice, the second derivative is negative 4. What does that tell us? Second derivative is negative 4. The second derivative is always negative. Negative is also a long word, so we have less than 0. But since the second derivative is always negative, we can conclude that f is always concave down. So now we can piece this together. Here, our only relevant value is over at 5/4. Our y-intercept is down here at negative 2. And now we just need to piece together the result. On negative infinity to 5/4, increasing, concave down. That's increasing, that's concave down. Put one of those there, go through the y-intercept. On 5/4 to infinity, decreasing, concave up, or decreasing, concave down, one of those. And here we have, well, it is a parabola as we expect, you know, because it's an x squared function. But here we have a local maximum. Also, we'll note, in those previous two examples, there was no local, or there was no absolute maximum or absolute minimum. This one does have an absolute maximum. You know, this y value, whatever that is the absolute maximum. But this one does have no absolute minimum. Yeah, absolute minimum, negative infinity, means no absolute minimum. But you know, this lecture has a lot of important information. A lot of the, well, all of the results are actually using the first theorem we had at the beginning of this lecture, which was a consequence of the mean value theorem. So all of this stuff we did, we are using the mean value theorem way in the background to reach these conclusions. But this graphing process, we worked only on some polynomials. It works for any function, but if I ask you one of these, which is likely, then it will be a polynomial, definitely. But I will post a document which has a few other graphs. I think the document's about 20 pages. It has the graphs. It also has all the calculus details.